Hey everyone, thanks for tuning in to the third demo. Today we'll be talking about visualizing and understanding optimization methods. Let's recall our three-step framework for understanding deep learning. We have a model, a loss function, and an optimizer. A model takes in data and, depending on some parameters, computes some output. Then we can compare that output to the output we actually want, and we call that a loss function. A loss function is always a single scalar value. Then we want to decrease the loss function by updating the weights. In this process, we refer to as learning. Of course, step one and step two, the model and loss function don't make sense if we don't have a good way to actually update the weights and thereby improve our model and reduce the loss function. So today we'll talk about different ways that we can, or different methods that we can use as optimizers. And I just want to emphasize that this step is absolutely crucial in deep learning applications because it's important that we're able to update our parameters so that we can improve the model and the loss. Today we'll talk about 4 different methods that are popular and well understood for optimization. The first is gradient descent, which is the approach that we've been discussing so far. It's very simple. You just take a step in the direction away from the gradient. There's Newton's method, which many of us have learned about in calculus. There's a multi-dimensional or multivariable version of it, which takes in second order information. But we'll see there are several disadvantages of this approach. Instead, we can use momentum, which is a very nice and clever method of keeping track of the history of where we've been so far. And then finally, atom, which is like a momentum, but adds an adaptive component of it. And atom for the last 10 or 15 years has been the go-to choice for an optimization method in deep learning. Atom is generally what we'll use in this class as well. Okay, so our goal is to visualize how each method works and discuss the advantages and disadvantages of each one. Unlike most demos, today it's not so important that you understand what the code is. In fact, I won't be coding it from scratch, and I don't really care if you even look at the code. The point really is to get a high-level understanding of what these optimizers do, and the code will just help us by plotting some nice function. So we'll, as always, I'm actually just going to run this all now. We're going to import some helpful functions, and then there's some fancy plotting code here. If you look at it, it's long and gross, and let's not look at it again. We'll just be using it to make some very nice, pretty pictures. Okay, so what is gradient descent? Gradient descent is a method of updating our parameters so that we are moving away from the direction of the gradient. And we do that by subtracting the gradient times some learning parameter. In our case today, so that we can visualize it, we'll be working with a very small loss function, which is defined on only 2 parameters, x1 and x2. It's a small 2-degree polynomial, and it's generally of this form: some coefficient a times x1 squared, some coefficient b times x2 squared, some coefficient c times x1 times x2, another coefficient d times x1, and another coefficient e times x2. We'll be looking at different types of loss functions, and we can get those different loss functions by just choosing what these coefficients are. But the particular choice isn't so important. The gradient descent update that we do, and the simplest algorithm that we're familiar with so far, is that we just simply update our parameters at the tth step of the process by taking the parameter we had at the prior step, the t-1 step, and subtracting off the gradient or the derivative of our loss function at that point with respect to the variable x1 times some learning parameter. And we do the same thing for x2. In words, the process is that the next parameter is the prior parameter minus the learning rate times the derivative. Now, this is kind of clunky notation, and it doesn't work so well when we have lots and lots of parameters, as we often do in deep learning. Instead of writing the update in terms of these scalar values, we can talk about the vector of weights, which I'll call this bold version of x, and it's simply a vector where x1 is in the first dimension and x2 is in the second dimension. Then instead of writing this clunky version of the gradient descent update, we can write it like this, where the new vector, the vector of weights at the tth time step, is the vector of weights at the t minus 1 time step, where we subtract off the alpha learning rate parameter times the gradient of f with respect to x. And we can see that these two methods are equivalent as long as we define the gradient correctly, which means that the gradient is this, has this form. Sorry, this should be, I used f, but really this should be L. And I correct it in both places? No, not yet. Okay, cool. I apologize. Yes. So if you're wondering what f is, you were correct. I didn't define it. It's in terms of this loss function. Did I do it correctly here? Okay. All right. So the gradient of this loss function is simply a vector, and the first entry of that vector is the derivative of the loss function with respect to x1, and the second entry is the derivative of the loss function with respect to x2. And whatever your dimension of your vector is, or matrix, parameter x, that's the same direct dimension as the gradient x. Okay, so this is our gradient descent update framed in this language. Let's visualize this process for a very simple loss function. We'll choose the loss function x1 squared plus x2 squared. Now you'll recognize this as simply a circle. We're used to the form where we have one variable squared plus another variable squared equals some radius squared. Here, we'll just define our function without setting it equal to a radius. So it's defined, and we can get a function value for any choice of x1 and x2. If we were to plot this function using contours or level sets here, we get something that looks like this, where our lowest value starts in the center, and then it increases as we move outwards in this circular fashion. And in particular, we have the same function value defined on this circle. So it's a very nice, simple function. It'd be great if we could always optimize this. And in this case, gradient descent works really well. So wherever we initialize this point, we take a step inward with a gradient, and we just keep going until we hit the minima. If we were to increase the point where we started at, so if we start at -6 and 6, for example, which is this point over here, it still works. We take a large step at first because the gradient is quite large, and that decreases over time until we get to the middle point. Okay, so far gradient descent is working really well, but unfortunately not all of our loss functions are this well behaved. In fact, as we increase the dimension, we don't really expect them to be this well behaved. So we can talk about another loss function, which is very similar. It's just, instead of adding x1 squared and x2 squared, we define it as x1 squared minus x2 squared. Notice that if we simply increase x1, the function quadratically increases, but as we increase x2, the function quadratically decreases. Let's try initializing our function as some particular point. So in this case, we can try x1 equals 2 and x2 equals 0. If we start at this point, then the derivative with respect to the second dimension is just 0 because it's 0 there. So we don't move at all in the x2 dimension. We only move in the x1 dimension. And in the x1 dimension, we optimize it, which is going to this point, which is called a saddle point. It's a saddle point because in one dimension, it's a local minima, and in another dimension, it's a local maxima. And if you were to put your hands together and visualize it, that's kind of what a saddle is. So if you imagine sitting on a horse and your legs are out from one side to another, then the saddle is the highest point of your legs. But if you imagine the horse's back, it's the lowest point of the horse. In this case, it looks like gradient descent doesn't perform so well, but if we think about this, it's really because x2 is initialized at 0. If we instead initialize x2 at a point like 0.5 up here, then we get good performance, which is what we expect. Instead of going straight to this local optima at the saddle point, we move away from it towards the global optima, which is outward at this point. Okay, so far gradient descent has been able to come through for the challenges that we have. But the thing that we've learned is that it's important to initialize gradient descent cleverly. So we never want to initialize some values equal to 0. Instead, what we want to do is initialize values randomly, and that way we're unlikely to fall into a trap of one of these local saddles. And oftentimes when we run an optimization method on a model several times, we initialize it randomly each time. And this is so that if we randomly get unlucky, we hope that we end up going to a local saddle point and staying there. We hope that that doesn't happen, and we just give it lots of chances so that hopefully on one of those chances it doesn't get unlucky, and we can do some sort of good learning process. Notice here it says intil, which is hilarious. We want initial point. Okay, I'll fix that later. Cool. Okay, so let's find an example where gradient descent fails. We can do it on a function that looks like this, which is, yes, very nasty. If we plot it, this looks somewhat familiar though. This is just an elliptical function. On this elliptical function, if we set the learning rate like we do to 1.5, we see that we get this very bad performance. Unfortunately, we start at some initial point, and from that initial point, we move in the direction of steepest descent, which is over here. And then from here, we do the same thing. We move in the direction of steepest descent, which is over here. But if you look at this process, we are wasting a lot of our steps and the direction that we're moving in because we're oscillating back and forth. So in this like diagonal direction, we're going back and forth, back and forth, back and forth. We are making progress towards the optimal solution, but we're quite inefficient. So something that we learned is that if we get weird performance with our optimizer, maybe we should try decreasing the learning rate. So if I decrease the learning rate and I set it equal to 0.5 instead of 1.5, then it looks much better because we're going in the direction of steepest descent very efficiently. But now this process is also very slow, and maybe we'll need something like 30 or 40 different steps in order to get close to the optimum. So it looks like we're at 30 steps, and we're not even close, or we're not even at the optimal solution yet. We're right there. The process is just slowed down because our learning rate is very small. So in this case, we have an issue, which is that if the learning rate is too large, we take a lot of steps which oscillate back and forth. But if we take a learning rate that's too small, we don't make much progress towards the optimal solution. Okay, so what's a solution here? Well, we can consider a different type of optimization method. In particular, let's think about Newton's method. Newton's method is something that we actually learned about in calculus. The idea was that we were trying to find a zero of a function, and we'd drop a tangent line and move to that tangent line on our function, and then repeat this process until we found the optimal solution. Under some conditions, such as if the function is convex or concave, I don't remember exactly which one is, maybe it's for both, then Newton's method works and it converges, but we don't have such nice properties here. And nonetheless, we may hope that Newton's method will work, or could work well for us. The Newton's method update in the higher dimensional case that we're used to when we have a function with lots of variables is given by this, which looks quite similar to what we had before, except we've just added this extra term here. This extra term is called the Hessian matrix, and this contains second derivative information. So the gradient contained first order derivative information is the derivative of L with respect to a particular variable x1. Here, the Hessian contains second derivative information, which is the derivative of our function L with respect to x1 and with respect to x1 and x1, the like second derivative of that. And we have all possible second derivative values here. So in particular, it's important to notice that the size of the Hessian is d squared, where d is the number of parameters we have to our function. In contrast, the gradient has size d, which is linear in the number of variables or parameters that we have for our function. So right off the bat, we notice that Newton's method is much more inefficient, much slower to compute and store than the gradient descent method. In particular, this is fine if we have very few parameters, such as 2 or 3 or 4 or 1,000 or something like that. But if we have tons and tons of parameters, like a million or a billion even, with models like ChatGPT, then the difference between d and d squared is very large. It's the difference between a linear rate of updates in computation, which would take, in the case of d equals a million, that'd be a million. But in the case of if we use something like the Hessian, it would be d squared, which is now, instead of like 10 to the 6th, it's 10 to the 12th, which is much, much larger, and it's not a scaling that we want. So we know we probably won't end up using Newton's method, but we're curious whether this gives us anything. In this case, it actually does. So if we consider the same ellipse that we did previously, or elliptical function, gradient descent is still not doing particularly well. It's oscillating back and forth, but Newton's method is doing exactly what we want. It goes straight from the initial point to the optimal solution directly, and this is because it has more information about the function. It can compute more about it, it knows more about it because it has the second derivatives, and it can just go straight to the optimal solution. But unfortunately, Newton's method also fails sometimes. And it can fail in the initial saddle point example that we had before. So notice here we have some initial point that's not at x2 equals 0. x2 is actually equal to minus 0.5 in this case. Gradient descent performs well. It goes to the global optimizer, which is way off in the top or the bottom. But Newton's method goes to the saddle point and stays there. Now, I didn't know why this was, so I wanted to look it up. The reason why it does this is a little bit technical. I'll explain it briefly, and if it doesn't make sense to you, that's fine. I just want to, if you are curious about it, I want to give you an explanation. The reason that it does this in this case is because you can think of this Hessian matrix, and you can take its, actually, we don't even need that here. So the Hessian matrix for this particular loss function, remember our loss function was x1 squared minus x2 squared. Well, I don't think it's actually 1, I think it's 2 here. Sorry, let me fix this quickly. If we take the derivative with respect to x1 twice of this, the second derivative with respect to x1 and x1 of this loss function, we get 2x1 and then 2. If we take the derivative with respect to x1 and x2, we get 0, because this would, the derivative of this with respect to x1 is 0, and the derivative of this with respect to x2 is 0. And if we take the derivative of this with respect to x2 twice, we get minus 2. So what you see is we get a minus 2 on this diagonal, and this minus 2 cancels out with a minus here that we're already subtracting off. Now, the issue with this is that we then take update steps, which move towards the saddle point instead of away from it, where we get a minus, we're subtracting the gradient, but it's actually a minus twice because of this minus 2 here. And the update that we have at this point is increasing. It's a step towards the gradient, which is in the wrong direction. And we can also see this if we increase the starting value to minus 3 and 1, like slightly further away. We'll see no matter what, that the initial point is moving, or that the Newton's method from the initial point is moving to the saddle, whereas gradient descent is moving away from it. And it's because of this undesirable property here, where we take the second derivative, and if it's negative, we cancel out the direction that we actually want to move in, and we move towards the direction of steepest ascent. Okay, so we've established two problems with Newton's method. One is that it's attracted to saddle points, and the other is that it's very time consuming and difficult to compute because we need order d squared time and space instead of order d. One approach to kind of simulate the advantage of having Newton's method is that we can keep track of the history of all the gradient descent updates. In this case, it kind of solves the problem that we had previously, because in some sense, the issue is that we had a memoryless process. We were here, and then over here, and then over here, and over here, and over here. And if we stopped and thought about it for a bit, we might realize, oh, maybe I shouldn't take as large of a step in the same direction I just came from. Maybe I should only take a step in the direction I've been moving this entire time. And the momentum method formalizes this intuition. In particular, we have some intermediate vector v, which is a weighted average of the gradient at this particular step, the xt step. Yeah, I should update this because this is the derivative at the x t minus 1 step. And I average that with everything I had previously. Here, beta is a factor between 0 and 1, so that if I have a smaller beta value, then I care less about where I was previously. And notice that if you expand this expression out, all the prior values, so 2 steps ahead previously get multiplied by beta squared, 3 steps previously get multiplied by beta cubed, etc. And because beta is less than 1, this decreases very quickly. So we keep track of prior history, but we more heavily weight towards things that happened more recently. Now that we define this intermediate vector, vt, I think this should all be, yeah, I'm not sure. Yeah, we can then update where we're going at this next step based on the direction, which is where we were, the gradient, the step, and the gradients at all the steps previously. Notice that if beta is equal to 0, then we don't take any history and we just recovered the case that we had before of gradient descent. This performs very well on our function that we have now, except there's one problem with this, which is that we don't change the step size very much when we're doing this process. So for example, let's set the learning rate equal to 1.5. And we can see that we do this weird thing where, so of course, gradient descent doesn't perform well. And the issue with momentum is that we've overshot the optimum and we need to keep going for a while. Let's try 20 more steps to get back to it. So it needs to do this weird looping thing. And this looping thing is very inefficient. Notice that we could solve this if we had a smaller step size when we got to this point. So instead of overshooting it with these large step sizes, if we could somehow know that we want to decrease the step size when we get here, then that would be very useful for us. Or actually, if we want to decrease the step size all the way back here so we don't have this large arc, and then when we get closer to it and we're approaching it with a straight line, we can decrease our we can correspondingly increase our step size so that we can do better there. Okay, so let's do this in practice. I won't write out the actual mathematical update here because it's quite messy, but if you want, you can visit this paper, which proposes it, and they have this nice algorithmic description here. See, it is quite messy in this update. So they keep track of momentum, and they also have this way of keeping track of the magnitude of all of the gradient updates. And the idea here is that we have, if our gradient has been very large so far, then we take the smaller steps. And if our gradient is very small and we're approaching this point, then we take larger steps. So relative to gradient descent, let me add it back. Cool, that worked. Oh yeah, maybe let's try 1.2. Okay, that's a bad example because it doesn't, okay, so I want 1.6 and then for gradient descent, I want to give it something like 0.5. Okay, so in this example, we are taking smaller steps initially than this one, which is good because we don't have to do as much out and back. We're still going faster than gradient descent because it's taking lots and lots of steps, but we're kind of doing the right thing, which is initially we take larger steps, or sorry, we take smaller steps so we don't have to do this out and back thing that we do with just momentum. And then as we approach the optimizer, instead of taking smaller and smaller steps as we do with gradient descent, which happens because the gradient is so small, we take larger steps. And these larger steps are because the magnitude of the gradient is smaller, so that we know we need to make more progress towards the optimal solution. Okay, this is kind of a hand-wavy explanation of Adam. Of course, if you're very curious, you can read more about it in the original paper, which in my opinion is quite readable. But kind of the takeaway, the thing that we want to discuss today is that like there are different advantages and disadvantages for each one of these optimizers. The advantage of gradient descent is that it's quite simple, but of course we can get this oscillation behavior, or it could move way too slowly. In terms of Newton's method, it can perform quite well in some settings, but in other settings it's attracted to a saddle point, which is quite unfortunate. And the space and time that we need to compute and store it is quite large. It scales quadratically with the number of parameters or weights we have, which just doesn't work for our modern deep learning models. We have a momentum approach, which keeps track of the history, but we saw that we can overshoot this. We can solve that solution somewhat with ADAM, which its name comes from adaptive momentum updates. So we combine the best of the momentum with the best of the idea of updating our learning rate adaptively, or the step size that we take, so that we zero in on the optimum, and as we're zeroing in, take slightly larger steps towards it. Okay, is there one right choice of optimizer? No, there isn't. And kind of the problem is that we can't do this analysis for the case that we care about with very large models and lots of parameters, because we don't have a way of understanding or visualizing these models in such a high dimensional space. Like the max of what we can reasonably understand is basically 2 dimensions, or maybe even 3, if we push it into a 3-dimensional graphic. But 4 is completely out. So what do we do in practice? Well, most of the time, people just try different loss functions and see which one works the best. Oftentimes in papers, people give an intuitive motivation for why their function is correct, or they explain that in some special cases, it has these nice properties. In general, the community has come to agree that ADAM is a very good choice, and it's now quite common to use ADAM as the optimizer in the 3-step framework that we know and love. And in this class, we'll basically always use stochastic gradient descent or ADAM. And I hope that after watching this and looking at this Python notebook, you have a better understanding for why it is that we chose ADAM and some of the advantages or disadvantages of several different approaches. Thank you very much, and see you next week. Reminder, if you want to come in person, please do. I had a fantastic time today with the group of people that came, and I think it's much more fun so that we can engage in person, and you can get your questions answered live in real time.